insert it into our finite difference time domain. We just put a diode here, which is a nonlinear element. We have a voltage source there and a voltage source here. We have a terminating we have an internal resistor there is equal to 50 ohm. The same thing here. We have a signal with 100 megahertz coming out of this voltage source. And this voltage source doesn't have any signal coming out of it, so it's basically acting as a terminating or a matching circuit at the very end.
Dr. Atef,
Yes.
the diode, did you try to have a physical model of the device instead of the X parameters?
The physical model is basically to have the actual configuration of the diode. Yeah.
Material and everything, right? Yeah.
Think about an integrated circuit. How many transistors there? How can I represent each one physically into a simulator like this? They never do this. I asked this question to the people who work with in industry and designing ICs and chips and stuff. They never do this because there is no way you can look at each one physically, put it there with million transistor and simulate it. So that's why they look at the behavior configuration of the entire, yeah. It is possible, and many years ago, Loopers, who published one of the first book on finite difference time domains, using something like this, is to take the resistor, inductor, capacitor, and represent it in terms of material properties as a cell itself. But that technique is not going to work right now. Yeah, yeah. Thank you for asking question while I'm presenting. So basically, please raise your hand. Yeah, raise your hand. That's good. I learned from the questions. Yeah. So this is the simulation, and this is the image coming out of our own finite difference time domain, exactly as you see it here. This is the equivalent ADS simulation for this configuration, and we started to capture the voltage as a function of time at port 1, and actually, no, this is the input voltage here, and you can see the input voltage has a fundamental frequency, and we are putting some small signal or trickle into the system as well with 0.01 relative to 1 here to basically excite the small signal and the large signal into the nonlinear device itself, which is the diode here. So these are the results, the finite difference time domain results, and you can see here the time domain response for port 1 and port 1 based on finite difference time domain and ADS complete. And this black curve here is a input signal coming out of the source. If you look at port 2, you also look at it in time domain from finite difference time domain and ADS. This is the voltage and this is the current, and that's basically what you expect from the voltage and current that comes here due to the diode with this orientation of the diode clipping of the voltage going through it. So we can capture the voltage and current in time domain, as you see it here, and we can transfer it to the frequency domain, which is discrete Fourier transform that we use. And basically the A wave, after some mathematical manipulation, and the B wave for the corresponding current and voltage are basically represented by these equations. So simply, once I can capture the voltage, because this is the time domain voltage and current, I can capture it easily from the finite difference time domain simulation. I can convert it to frequency domain. Remember, the A wave and B wave for a nonlinear device are frequency domain component. That's why I have to convert this to frequency domain. And then and they are represented in terms of voltage and current. So basically, I use the expression that came out of the finite difference time domain simulation to basically construct the A and B wave. Once I construct the A and B wave, then the X parameter for this device is already defined. I can have it as a black box. So basically, this is the first X value comes from the B wave. And if you look at the representation of this B wave that's been extracted using the finite difference time domain and ADS, you can see a perfect match here. And that's the amplitude. And that's the previous one was at port 1. That's the reflected B wave. And this one, the transmitted B wave at port 2. And you can also see a very good match between both of them. So for this simple device, we use ADS because ADS is going to allow us to confirm that our mathematical formulation and implementation in finite difference time domain would be accurate or not. But once we make this confirmation, we can continue with much more complicated devices there. Okay, so I showed you something for the large scale experimenter. We can also extract the small scale or the small signal experimenter if we basically repeat the simulation many times with multiple small signals coming into the device. Okay, now how do I integrate this black box into the finite difference time domain for a completely different simulation? We are going to have to, since the black box is a function of a B wave, I need to create a wave port in the finite difference time domain, and I need to be able to come up with an updating equation for it. So if I use a nonlinear device as an equivalent circuit, I can represent it in the finite difference time domain as a lumped element method. And I gave you the equivalent circuit for JFET transistor before. So we can do it this way, and we can take the B wave and X parameters that we extracted and put it between these two ports and run this simulation. I'm going to call this lumped element model, and this is the X parameter model to see if we can come up with the same solution or not. For large scale analysis, we use only the first term, and obviously I would like to create some sort of a B wave here, like the J current that I had it along this side, along this edge. You notice this symbol here, because this B is a frequency domain parameter. In the time domain, I'm going to have a B wave with this delta here, or this symbol here, to represent a time domain B. So from time to time, I have to switch between both of them to be able to come up with a solution. I showed you how we integrate any other elements based on the J current going through this edge here if we are solving for easy here. And this is the discrete Fourier transform between the frequency domain B to the time domain B. We extracted already the B wave from simulation, or we get it from measurements. And we know that the time domain B wave is going to be equivalent to this expression that has a voltage and has a current. The voltage can represent an electric field, and the current I can represent in terms of magnetic field, and I can substitute them there. And once I substitute them there, I can solve here. This is the B wave expression. I have the voltage and current. From this equation to this equation, I'm interested to get the current. So I solve for the current. That's a function of the B wave. Why I'm doing this? Because I know that this is an updating equation that's already been established and is already been known for any kind of source that's going to be along this edge. So I need to get the equivalent current that corresponds to that B wave to be represented here. And that's why we ended up with the current in terms of the B wave. V can be represented in an electric field. First, the current is normalized by, is divided by the cross-section area to give us the current density. And here the voltage is going to be replaced by electric field average. So it's the same equation. And then the final equation is going to end up with the updating of the electric field is in terms of the time domain B wave that represents a large scale signal of a nonlinear device along this edge. So this is the expression of the B wave. This is the expression if I have a current density that represents any other nonlinear device. A very similar expression in terms of form, and that's how we would like to do it, because we don't want to change the formulation of the finite difference, updating equation of finite difference time domain. All what you see is that the coefficients that are multiplication of E and H field component are different, and those coefficients you calculate them first before you start your time iteration. So, so the point here is that to be able to represent a B wave in a finite difference time domain, and that's basically allow us to integrate an X parameter black box into the simulation. So to confirm that what you are doing is good, we are going to look at this problem here. We are going to solve it as a lumped element, and we're going to solve it as a B wave integrated into the system. This is the lumped element configuration coming out of the simulator. And the equivalent circuit of this transistor here is going to be represented by these two combination of dependent source and diodes. And each one of them are going to be represented by a specific updating equation placed into the between the two microstrip lines here. And let's look at the results. Based on the lumped element and based on B bias for this simple configuration. This is the input signal with 10 millivolt peak value, and this is the output signal. This is the input signal here with 10 millivolt sinusoidal signal, and then the output signal coming from B-spice and finite difference time domain using the lumped element is basically, you see it here. You notice that this level is 10 millivolt, but this level here is 1000 millivolt. So obviously that level here is much higher than 10 millivolt, and you can see about 17.4 amplification due to the presence of this amplifier here. The other thing you notice here is that the output, which is a sinusoidal waveform here, is stabilized after maybe about 160 nanosecond. We were suspecting that what we are doing something wrong here, but B-Spice also predicted the same trend. Nothing has happened to give you the right performance of the amplifier as you would expect it until after about 160 nanosecond. So that confirms that if we use this equivalent, this circuit. Yeah.
Let's go back for the
this one?
Yeah, no,
Before.
This?
the one you try to amplify the signal.
The output.
Yes. Does it also increase the amount of noise?
Say it again.
My question is about the noise. Is
The
it
noise.
also, increasing according to the amplification of the input?
So you can look at the noise at those small tickled signal that is going to go into the system. And for this, we need to have the small signal representation of the X parameter. But at that time, in this confirmation, I'm only using a large signal component of the X parameter. Okay? I just wanted to confirm that the circuit as I represented here, when I put it in finite difference time domain, I can get the right response for it, because after that, when I, so this is again showing you where the steady state condition is. After that, when I put the B wave into the finite difference time domain simulator, I need to compare it with something I can trust. So basically, I trust this lumped element model. Now, this is the simulation. Use the lumped element model that you have seen it before, and this is the X parameter simulation. So I extracted the B wave, insert it into a finite difference time domain, and you look at the X parameter response. It's a complete sinusoidal form all the way from 0 time. A huge advantage in terms of having the device to act immediately as it's supposed to be right away. You don't have to wait. And you can see it is stable all the time. The lumped element and the B-Spice was not stable from the very beginning. Okay, and this was done with a signal that has 10 millivolt. Now, if I increase the input signal to 100 millivolt, this is the response coming from finite difference time domain and B-Spice, again to confirm that it's accurate. And you can see that the output signal is no longer sinusoidal. So the nonlinearity of the device has started to show up in the output. And when we do this also using the X parameter or the B wave, we can compare the lumped element model and the X parameter model. And we compared it at 1 millivolt, 10 millivolt, and 100 millivolt. And you can see a perfect, almost perfect match between 3 of them. Now, the last one here, 100 millivolt, you did mention if we increase the voltage, we are going to get some noise. You can see a little bit of difference. And I'm going to comment on that difference as well. And to give you a hint, what I'm going to talk about it here, those small difference comes from the small signal, and the small signal is represented by a series, double series, and the double series has different harmonics. So basically, if you don't consider all the harmonic in your extraction of the X parameter and use an X parameter that depends on only few harmonics, and then plug it in, compare it with another solution that has all the harmonic effect, then you are going to see some difference. I'm going to also illustrate this later on. And that's basically showing up here. You can see the amplitude of the amplification and the phase of it. We can see a perfect match up to the fifth harmonic. Beyond the fifth harmonic, we don't have a perfect match. And why is this? Because in this equation here, way back, yeah. This would be sufficient. This represents the port, and this represents the fundamental harmonics. So when we extracted the X parameter from the finite difference time domain, we extracted to 5 harmonics only. So the X value that we used it in the simulation later on is going to give us results accurate to the fifth harmonic only. And that's why you see a big difference beyond the fifth harmonic. Yeah, you can see the results are basically matching very well with the lumped element model, only up to the fifth harmonic. Okay, so so we can get good results by using a specialized port and simulating the P wave. The method was limited to a larger scale, but we updated it to smaller scale or small signal analysis as well. So let me show you also how we can use the X parameter as a black box without knowing the P wave. And that's basically, I'm going to have a black box between these two ports here, port 1 and port 2. And again, we're going to go back to the definition of A wave and B wave. And basically, the X parameter represented in terms of X, FB, and XT and XS. This we know that A and B are function of voltage and current. I can extend A, which basically be in this term plus this term, because you can see here A has this term and this term. So now if I start expanding A in terms of E and H, you are going to end up with the A wave is going to be coming with an expression like this that has nothing, or doesn't have anything other than E and H component from the electromagnetic simulator. How many more minutes? 5? Okay, 4, okay. So the expression of A and expression of B are very similar. They are now in terms of E and H, but you notice that we have the symbol on top of them because they are time domain A and B waves. I can simply convert them to frequency domain by discrete Fourier transform, and also between time domain and the frequency domain B wave. And then let's look at the X parameter expression itself. So this X parameter expression, B in frequency domain, which is here, this is the time domain signal, time domain B wave, and basically we get this, the time domain signal in terms of related to this expression here in this form, and we do some mathematical treatment for this. We are going to end up with equation like this, in which we are going to see that the updating equation of EZ at the future time is represented in this equation, and we have also a term here that has the future time. So I need to get this to this side and manipulate this equation. I can put it in a matrix form like this. And this matrix for the M itself is going to be a matrix that I can evaluate. And the B non-term is also much more complicated. I mentioned to you that I have to use equation here to represent what we are doing. And then we are going to solve for x, and x basically is our future value of EZ. So this is basically the process in between updating equation here. We capture electric field values for x parameter updating, and we solve the matrix that I showed it to you here in between the time iteration, and this way we managed to be integrating a black box into a finite difference time domain time loop. So to show you some results, again, you can see the lumped element representation, the x parameter black box. That's the B2, and this one B2 phase and amplitude. And again, let's see that the input signal was 100 megahertz. The fifth harmonic is 500 megahertz. That's why you have accurate results only to 500 megahertz, because you use only 5 harmonics in the analysis itself. This is a small signal, XS, amplitude and phase. And I think the previously was B wave itself. So I didn't show you the XT as well, but it's very similar results. So this is basically what we have done. We managed to be able to characterize the behavior of a nonlinear device, extract the x parameter from a finite difference time domain simulation, use this extraction into a black box, and being able to put it in a finite difference time domain simulation and run simulation and confirm the results. Is this work finished? By all means, no. All I have shown you here is basically a very simple sinusoidal waveform coming in. In most of the application, we are going to have a pulse or a signal. So there is additional work that needs to be done here. And the code that was written as is right now is not optimized, written in MATLAB. So there are lots of work to be done. However, I think it's a very good contribution to have here so far. There is still some future work. I would like to mention that these are some of the conference papers that we publish through this work. And these are 2 journal articles. And also we have the first chapter in this book that's actually came out online and is going to be available in 2023. And the first chapter in this book is basically addressing all the things that I discussed here. I would like to thank 2 people. Peter Owen is my colleague in the department, who is mainly specialized in transistor measurements, evaluation, and design. And Kate Rimley is from NIST, National Institute of Standards, and both of them provided helpful discussion and throughout the work. I welcome any questions.
No. I have a simple question. Thank you. First of all, thank you very much.
Thank you.
I would like to ask, are the analysis and simulations irrespective of the transistor mode of operations? I mean depletion mode, enhancement mode.
No, we
have
have
you
to
considered that?
We have to be in the mode where the transistor is being used as an amplifier in the circuit. Yeah, of course, that question is very good, because this is reflect on what I mentioned before. When we use an equivalent circuit for some transistor and we put them in the finite difference time domain simulation, we didn't get a stable code for all these conditions. So it depends on where the input and output of the transistor are getting the transistor to work in a specific stage that can be simulated with finite difference time domain. Yeah, thank you.
Thanks for the fancy presentation, actually. And I'd like to ask about the difference between the experimental X parameter model that we can extract from the measurements and the behavioral model. If we have the experimental model, in which cases we have to go to the behavioral model, and
well, the measurement is giving you the behavior characteristic of the device.
That's right. So if I have the X parameters based on measurement, this will be enough.
Be enough for what?
For the integrability.
Once you have the X parameter, you can cascade it.
Yes.
But if you would like to put it in a electromagnetic simulator. If you use the current method, is basically you are going to solve the electromagnetic problem by itself, and then you are going to tie it to the nonlinear X parameter of the model, and you are going to go back and forth.
Yes.
If you don't want to do this, then you do what we just presented, is basically to integrate the X parameter into the Maxwell equation into one simulator.
Great.
Okay.
Thank you very much.
Yeah.
Last question. I think there is some.
I have a question about the transmission lines used to connect the elements. Is it taken in consideration the parasitic capacitance that's produced by those transmission lines and can be formulated with the finite difference time domain?
The answer to this is basically the transmission line is being represented by actual conductor and spacing between them. The media is characterized exactly, and all those parasitic element or parasitic effect are integrated into the full wave simulator.
Okay.
I don't have to represent it as separate element as a circuit model.
Okay, thanks.
Yeah.
Thank you very much, Dr. Atef.
Yeah.
However, I'm not expert in the field, but I get some knowledge. Thank you very much. So my question is it possible to transform your model from the MATLAB to Python, because Python now is a very fast one, and you can easy edit your code, and also it's free. So you can. I mean it's the community of using Python can help you more to improve your code if you transfer it from MATLAB to Python. Thank you.
I can answer this question. Our first book in 2009 has all the codes in MATLAB. In the second edition of the book, 2015, we have 4 more chapters, and we have a dedicated chapter on how to put your code in CUDA, in C and CUDA, and run it on the GPU. The image I showed it to you here are coming out of our semi-commercial code, which basically C, CUDA, and Fortran, and we managed to be able to reach 10 billion second execution per second on a single GPU card on a single computer. And with this single GPU card, we can do up to 600 million cells in the domain. So there is no way that Python is going to give us this capability. I'm not planning to convert MATLAB into Python. Sorry. Okay.
Yes. Thank you for your presentation. I want to ask about, I am interested in active antenna. I want to ask about when we find your software finite difference time domain.
You can have the MATLAB software out of the book. It's completely there. Yeah.
Yes, but I want to see some easier way to find a library of your transistors, amplifiers, and I put it in the chart and make a simulation.
We just finished this work, so we didn't create any library for nonlinear element yet. Yeah.
Yes, I hope to see that.
Well,
yes,
that would be good. We can get one master student, he can generate those. Yeah. Good comments. Thank you. Yeah.
Dr. Atef, with your experience, I have a loud sound. So with your experience with the FDTD being expert, basically in the antenna community, we rely more on CST and HFSS. Both of them are not FDT based.
No. CST is a finite integration technique. Yes. It is basically the same. They are using integral form of Maxwell equation to start with. We're starting with differential form of Maxwell equation.
There was at certain point the XFT.
Yeah.
There are some commercial. How are they doing? Probably you are.
All of them are doing very well. Owners are getting very rich. We are not. The main attraction for all these software is the input interface. They have manpower, they have engineers, they have huge manpower to develop the input interface. Our code is basically developed by myself, one of my former students who is now associate professor, and just between two of us. So basically we use